Okay, so hello everyone, welcome back to my YouTube channel. So in this video, we will try to solve this integral here. I encourage you to try it first by your own self. Just do everything you can to solve this integral first before continuing continue playing this video. So yeah, pause the video and try. Okay, so let's get started. So here we have this integral here, and at first I definitely agree with you that this seems annoying. Why? Because first, we cannot use, of course, we cannot use direct substitution here because we have something weird. And when we use substitution, no matter uh, whether you substitute the secant theta, or I mean the denominator or the numerator, or even both, you will end up with messed up. You will mess up your problem instead of solving it. So the key is we need to do some manipulation first before we apply several techniques that will help us to solve this. So first, since we already have this term, so I think it is a good idea to make it as secant squared theta minus 1, because recall trigonometric identity equation. So let's do this. So here we get secant theta minus 1 over secant squared theta minus 1 d theta. And again, as I mentioned before, we have something like this, which yields so we can change the denominator into okay. So first, before we continue our step to solve this integral, so let's think first about kind of approach that we need to execute to solve this. So when we look at the secant theta, we know that secant theta is equal to 1 over cosine theta. And here we have tangent at the denominator. So we have sine squared theta, like secant theta minus 1 over sine squared theta over cosine squared theta. So if we split the numerator, and which means that we will have two different integrals, and for the secant theta part, we will have something like 1 over cosine theta times cosine sine squared theta over cosine squared theta. So I think that's a good idea, and that's a very good beginning to solve this integral. And also we will have minus integral of 1 over tangent squared theta, which is just like the integral of cotangent squared theta with respect to theta. Okay, so let's see. If we split the integral to be two different integrals, again, 1 over tangent squared theta is equal to cotangent squared theta, and secant theta is equal to 1 over cosine theta, so we'll have okay, so this one is definitely cancel. So we have Okay, here you go. So let's save this as equation 1. I think we are getting smaller here. Yeah, I think we are getting smaller. Let's just make this bigger instead to keep it consistent. Okay, yep, that's, I think, looks better. Okay, now let's do the integration separately. First, let's do for this part. So here we have this, and as you can see, this integral looks like tell us to use a direct substitution where we substitute u or maybe other dummy variables as whatever you like to be sine theta, and when we take the derivative of it, we will have cosine theta times d theta, which is equal to d of the variable that you choose. So here I will take c. This will imply perfect, so we can just substitute the dz here and the z here, so we'll have just like write it. From the integration power rule, we will get where z is equal to sine theta, which gives us the negative of 1 over sine theta, and 1 over sine theta is equal to cosecant theta, so we'll have perfect. So now let's do for this integral here. So recall that cotangent squared theta is equal to cosine squared theta divided by sine squared theta. So we'll get, and if you notice, there is something that might familiar to you. So if we split the theta of the cosine squared theta, we will get this. This term really looks like this, right? So this seems suggesting us to use integration by parts. So let's do that. So here we have, which is equal to this. So since we already know the integral of cosine theta divided by sine squared theta, we can just assign it as dv, because we already know the integral when we try to find v, and let u become cosine theta. This will give us here, and for this one, the dv, where we have already found the integral, which is equal to minus cosecant theta. That's the v. Wait, let me just write it more nicely. Okay, so let's do this. So the integration by part formula is integration of u times dv equals to uv, which is equal to cosine theta times the negative of the negative of cosecant theta. So wait a second, we are not substituting cosine here, we should substitute sine instead. Oh, no, not that. My bad. Okay, continue. So we will have u times v, which is the negative cosecant cos theta times cosecant theta, where cosecant theta itself is just cotangent theta, cosine theta divided by sine theta. So we will have just like rewrite it directly, cotangent theta minus the integral of this phi du, which is sine theta times cosecant theta. Again, it cancels each other because cosecant theta is 1 over sine theta, so we'll end up with only theta, d theta I mean. So this give us minus cotangent theta minus theta, which is perfect. So we can just directly plug all of these to equation 1. So we will have just write it as 2, 3, we will get that the integration of secant theta plus 1 is equal to minus cosecant theta. Is that correct? Yeah. And plus cotangent theta plus theta plus c. Don't forget the plus c because we are doing indefinite integral here. Never forget that. So there you go. This is our answer. So you can verify it by taking the derivative of our answer, and it should give you our starting point here. Okay, that's the idea of integral, which is the antiderivative of a function. Where in here we just find the family of functions, the family of this function, which differs with c, with respect to c. So hope you guys found this video helpful, and consider to subscribe my YouTube channel for more incoming physics and mathematics content. And don't forget to like, leave a comment, subscribe, and hit that notification button so you can get updates from my YouTube channel, and share this video to your friends. And hope you guys have a great day, and thanks for watching. See you on the next video.